In this chapter, we're going to continue talking about acids and bases, but we're going to get into the calculation side of it. The two things we're going to talk about are pH scale and then titrations. pH scale, you've probably heard a little bit about. Titrations, probably not. We'll talk about it some here, and I'm sure we'll spend a little time in class together talking about it. So first of all, the pH scale. pH scale runs from 1 to 14. There's some other little quirky things that we'll deal with on the pH scale, and then maybe some things we kind of avoid. But here's the general concept. If something is acidic, then it's got a pH of less than 7. If something is considered a base or has basic properties, it has a pH greater than 7. We've learned last chapter, remember, acids have H's, bases have OH's. Something that is neutral, we say has a pH of 7. A couple other things just to remember here as we start doing some calculations. Hydrogens, these hydrogen ions that come from acids, can also be written as H3O+. That's very important that we don't get this confused. This is what's called a hydronium ion, H3O+. If we notice what H3O+ is, it's really water plus the hydrogen added to it. The significance of this, again, these hydrogen ions are dissociated, they dissolve, they're loose. A lot of times they will attract themselves to other hydrogens. Now we don't see that written for hydroxide ions, or the OHs. When we're talking about bases, we just see it written as OH. We do not see it written as OH with water. So you're never going to see this H3O2- formula. So which is correct? Both of these are correct. The H plus as well as the H3O, but we won't see that occur for the hydroxide ions. Next thing, when we're doing all these calculations, we are going to be using molarities, not molalities, just molarities. So we definitely want to remember how to do these calculations. Remember, the definition of molarity is the number of moles of chemical that have been dissolved in a liter of solution. Those are what we're going to use to calculate the pH. So when we say the pH is 2 or the pH is 5, that comes from molarities. So what we're going to be looking at is we're going to get information that looks like this. The concentration of hydroxide, or the concentration of H3O, is equal to, and we are going to see some small numbers. Okay, we are going to see some numbers times 10 to some negative exponent, just for the purposes of what we're going to deal with. So again, we haven't done any calculations yet, but we just need to know, be prepared for what we're going to see, so we know how to deal with it. Okay, so we'll be looking towards seeing a lot of molarities in these calculations. Now, a couple other things here just about pH and pH scale and what does it mean. So a pH scale, we already know what that is. A pH scale goes from basically 0, even though we sometimes say 1, to 14. 0 being an acid, 14 being a base. Now, we can also have what's called a pOH scale. Basically, it's just a scale in the opposite order. If it has a pOH of 0, that means it's a base. If it has a pOH of 14, that means it's an acid. Well, which one are we going to use? Well, we use the pH scale, but it is important to have the other scale just for some purposes. And here's an important number or little equation to remember. Whatever the pH is plus whatever the pOH is has to equal 14. That has to be true. The pH is 0, the pOH has got to be 14. If the pH is 1, the pOH has got to be 13, so on and so forth. So again, we've got a couple other things here just as reminders what that means. So if we have something that's acidic, its pH is less than 7, its pOH is greater than 7, and we have more H pluses than OHs. If something is basic, the pH is greater than 7, the pOH is less than 7, the amount of hydroxides is greater than the amount of hydrogen ions because we got more base. And then if something's neutral, the pH and pOH are both 7s, and then the concentration of those two ions is equal. Nothing too crazy here, but some things we definitely got to know. Now the next thing we're going to talk about definitely explains why the pH scale is what it is. what the numbers mean, how do they get 7 for neutral, how do they get 0 to 14, all that stuff. So we'll briefly kind of talk about it. Fully expect to have to spend a little time in class reviewing it too. So we're going to talk about what's called the self-ionization of water. So water can actually act like an acid or a base. Right? We talked about the concept of amphoteric. So here's what we're going to do. We're just going to look at 2 reactions, one of which water looks like an acid, and one of which water looks like a base, and one where some of the waters don't change. So if we can imagine we got waters, a whole bunch of them. Some of them are going to act like an acid, some of them are going to act like a base, and some of them are going to act like neither. They're not going to change. So what happens is the ones that are acting like an acid end up losing a hydrogen, and they become hydroxides. That hydrogen that leaves here ends up going to the H2O, and that H2O becomes an H3O. And then lastly, we have the majority of waters don't change. So they discovered this phenomenon that occurs, that water has this unique property. It's not a strong acid, it's not a concentrated acid, it's not a strong or concentrated base, but they did measure this. So here's what they found out. They found out in terms of concentrations, this is the molarity of hydroxide and hydronium ions that are actually produced. So if we look at that molarity, that's small, 1 times 10 to the minus 7. Extremely small concentration, probably one of the smallest ones we've seen at any point in time. So what this talks about how we can this leads into how we're going to talk about the calculations for pH. So what this led to next was what we called the equilibrium constant, or the ionization constant. And what this value is, it's what we call the Kw. So the Kw for water at 25 degrees Celsius is 1 times 10 to the minus 14. So Kw equals H3O plus times OH minus. And this number is unique to water. So what it's basically telling us, that number is really, really small. It's basically saying that we have an extremely small amount of water that changes. But we do have some that changes. And that's the number associated with it. So here's the connection to the pH scale. What they determined was this right here. If a substance has a concentration of H pluses or H3Os greater than that number, if it has more H pluses than water, and that's water's number, we're going to call that chemical acidic. If it has a concentration of less than that amount of hydronium ions, then we're going to call that basic. Again, it goes back up to these 2 numbers right here. If a chemical has more than or less than either one of those numbers, that's how we classify it as an acid or a base. We'll get into the actual calculations here in a little bit, but this is important. Water does change like this. Not very much, but it does. So this is the line that they've drawn, that the chemists have drawn to create the pH scale. This number here of 1 times 10 to the minus 7 is the concentration of H plus. If it's greater than that, then it's acidic. If it's less than that, it's a base. So here are the bases, here are the acids, and that's everything that's neutral, chemically neutral at a 7. If the concentration of hydroxides is greater than that, it's a base. If the concentration is less than that, then it's an acid. Okay. So, and actually this one back here, if it's less than, that's what should be a base. So if we have an amount greater, if this chemical has an amount greater than 1 times 10 to the 7, it's a base. If the chemical has an amount less than that, then it's an acid. I know we'll probably have to talk about this a little bit more, but this is where the pH scale came from. The next thing we'll look at is how do we actually calculate pHs and be able to do some of that stuff.